Astronomers, using the powerful James Webb Space Telescope, have uncovered a cosmic anomaly, a massive galaxy that challenges everything we thought we knew about how galaxies evolve. This newly discovered barred spiral galaxy, named J0107a, existed 11.1 billion years ago. Yet astonishingly, it already featured a large, fully developed central bulge and was 10 times more massive than our present-day Milky Way. How could such a colossal and mature structure form so early in the universe's history? This unexpected twin of our galaxy has thrown current scientific models into question, and no one knows exactly how it fits. But the surprises don't stop there. At the same time, scientists revealed the most detailed 3D map of the universe ever created. And their findings suggest that one of the core principles of modern physics, the Standard Model, might be deeply flawed. In fact, it may even be time to take a fresh look at Einstein's theory of relativity. So what exactly have experts uncovered? And how could this reshape our understanding of the cosmos? Stick with us to explore the full story. Just weeks ago, researchers added a new structure to the cosmic map, Zulong. This mysterious formation is now considered the oldest known spiral galaxy, dating back to just 1 billion years after the Big Bang, and it's raising big questions for science. Despite its young age, the galaxy already had the mass and structure typical of the present-day Milky Way, a surprising discovery. According to current understanding, spiral galaxies need one crucial ingredient to form: time. Scientists generally believe that it takes billions of years for such complex systems to develop the defining features of a spiral galaxy. These include the central bulge, the dense core of the galaxy, and the sweeping spiral arms. Models suggest that shortly after formation, these galaxies begin as irregular star clusters, slowly flattening into a stellar disk. Only after several billion years do the spiral arms and central bulge fully emerge, or so we believed until recently. Zulong's puzzling find challenged that timeline, but it was only the beginning. Researchers have now identified another galaxy from the same era that doesn't just match the Milky Way in size, it surpasses it significantly. Remarkably, it's also a spiral galaxy, more specifically a barred spiral galaxy, distinguished by the central bar from which its spiral arms extend, just like our own Milky Way. Interestingly, this straight structure not only defines the galaxy's appearance but also acts as a crucial channel for gas flow, fueling the formation of new stars. Previously, scientific models proposed that such distinctive bars formed only in the later stages of a galaxy's life, leading researchers to believe that barred galaxies had only existed for a few billion years. However, this assumption has proven to be incorrect. Observations made by the James Webb Space Telescope about 2 years ago revealed that barred galaxies were already shaping the cosmos as far back as 10 to 11 billion years ago. One such galaxy, Sears 2112, emerged on the cosmic stage just 2 billion years after the Big Bang. Following the Big Bang, and possibly even forming around 600 million years earlier, astronomers have now identified a colossal barred galaxy from the early universe, Chryson J0107a. This galaxy is truly immense, surpassing anything previously observed. At 11.1 billion years old, it holds 10 times the mass of the Milky Way and boasts a star formation rate 300 times greater. This cosmic giant was discovered by a research team led by Xu Huang from the National Astronomical Observatory of Japan. The discovery relied on images captured by the James Webb Space Telescope and data from the ALMA Radio Observatory in Chile. ALMA allowed researchers to map the movement and distribution of gases within the galaxy, revealing that the galaxy's central bar is funneling massive amounts of gas inward from its outer edges. Astonishingly, this gas inflow occurs at a rate of about 579 solar masses per year, a dramatic contrast to the mere 0.01 to 50 solar masses per year typical of local barred galaxies. This extraordinary inflow helps explain the incredibly high star formation rate in the galaxy's core, which reaches up to 500 solar masses per year. Given these characteristics, Huang and his team describe J0107A as follows. This galaxy is the most massive barred galaxy from this era, even more massive than the largest galaxies in the nearby universe. J0107A stands as the most distant and massive galaxy with a fully developed bar ever observed. The rate of gas inflow is sufficient to drive intense star formation, and it may also be fueling the heightened activity of the central supermassive black hole. While those are the basic facts, we shouldn't overlook the reality that this early galaxy, J07A, defies several key aspects of our current models of galaxy evolution. One of the most striking contradictions lies in the element of time. Traditional theories suggest that barred galaxies evolve slowly and gradually, yet the advanced development of J07A turns that notion on its head. Even more puzzling is the galaxy's unusually high concentration of molecular gas. Around 70% of its mass is gas, while only 30% consists of stars. This imbalance poses a significant challenge to our understanding of galactic development. As astrophysicist Dan Fisher from Swinburne University of Technology explains, according to existing models, the gas-rich environments of early galaxies should have prevented bar formation. But the latest observations show us a well-developed bar structure and gas dynamics that weren't thought possible at such an early stage. In short, these findings directly challenge established theories. As is often the case in science, our models hold true, until a new observation forces us to rethink them. And with each new discovery, the James Webb Space Telescope continues to deliver such paradigm-shifting observations on a near-regular basis. What holds true on a small scale also seems to apply on a cosmic level. New research is now challenging one of the core foundations of our understanding of the universe. We are being forced to reconsider the idea that Einstein's theory of relativity is completely accurate. The once accepted cosmological constant is now being questioned. Today, we understand that the universe is not a static, unchanging entity. Instead, it has been expanding ever since it came into existence around 13.8 billion years ago. But this expansion isn't happening at a steady pace, it's actually speeding up. To make sense of this accelerating growth, scientists have introduced the concept of dark energy, a mysterious force thought to be driving this unexpected cosmic expansion. Our understanding of dark energy is, to say the least, still very limited. It hasn't been directly confirmed through experiments, and its true nature remains a mystery. According to the current standard model, dark energy is believed to have a constant density throughout time and space, essentially a fixed value. That's what scientists accepted for many years. However, recent findings are beginning to challenge this idea. Astronomical observations have uncovered major inconsistencies in the rate at which the universe is expanding, suggesting it's accelerating much faster than what Einstein's theory and the Standard Model predict. Even more surprising, evidence surfaced last year indicating that dark energy might not be constant after all. And now, that suspicion is gaining more support. So, what changed? The turning point came with new data from DESI, a research project in Arizona created specifically to investigate the mysteries of dark energy. Using the Dark Energy Spectroscopic Instrument, DESI, scientists have now examined data from more than 15 million galaxies and quasars, also known as active galactic nuclei, to produce the largest and most detailed 3D map of the universe ever created. To better understand dark energy, the team not only analyzed the redshifts of galaxies and quasars but also studied subtle patterns in their spatial distribution, specifically focusing on baryonic acoustic oscillations. These are ripples in matter density formed in the early universe due to the interplay between gravity and radiation pressure, which led galaxies and clusters to form at regular intervals. By measuring these patterns across various distances, researchers were able to infer the universe's expansion rate and track how dark energy influenced it over time.